Hello, this is question 15 on your AQA paper 1 from November 2021. In this question, you have to use G, 10 meters per second square. I could try to remember this because we usually use 9.8 and it's very easy to just forget. A box B of mass 4 kilograms lies at rest on a fixed rough horizontal surf. So this one. One end of a light string is connected to B, so here, and the string passes over a smooth peg, here, attached to the end of the shelf. The other end of the string is connected to particle P, mass is 1 kilogram, and is hanging freely below the shelf. Yeah. Then B is initially at rest, held at rest with the string taut. B is released, B and P both move with constant acceleration A. Yeah, so when this is released, this is going to move that way. As B moves across the surf, it experiences a total resistance force of 5 newtons. So B is moving that way. It has a resistance force that way, which is 5 newtons. State one type of force that could be included in the total resistance force. So they say the surface is rough, right? Which means part of this resistance force will be friction, and that's the only thing that you have to answer for the first one. So friction or frictional force. That's the first. Then second part, they say show that A is 1 meters per second square. So the acceleration, we have to find the acceleration. Remember with these questions that are a pulley, or in this case it's a peg that is not rotating, but it will work exactly the same. We have connected particles. What we can do is to write an equation of motion for this one, an equation of motion for this one, and then see what is missing and what we need. So for the hanging one, we have the weight pointing down. I'm going to write all the forces that I have. Will be 1 kilogram times G, so G, and the tension pointing up in the string. And for B, I will have the tension in that direction, is what is pulling and moving that way. And I have a friction, and a resistance force of 5 newtons. I will have the weight, which is for G, and a normal reaction, but we are not going to need anything in this direction, right? And then it's moving that way with an acceleration, and this one is moving down with the same acceleration, and we need to find that acceleration. So what we are going to do is to write an equation of motion for this one and an equation of motion for this one. So for P, it's moving down. If it's moving down, this force will be greater than this one, so I'm going to write G minus T. That's my resultant force. So I'm going to apply force is mass acceleration, so to both of them. So for P, I say that G is greater than T, so resultant force is G minus T, is mass, which is 1 kilogram, times acceleration. And for B, for the one that is on the shelf, in this direction, it's moving that way, so T will be greater. T minus 5 is going to be mass 4 kilograms times acceleration. So T minus 5 is mass, which is 4 times acceleration. The acceleration is the same. And we need to find the acceleration. So we have two unknowns here, A and T. If we solve the simultaneous equations, we will be able to find the tension and the acceleration, but they're asking just about the acceleration. So for example, I'm going to add them, because if I add both equations, I get rid out of the T, and I can find A straight away. So G is 10, I have 10, these two are gone, 10 minus 5 is going to be A plus 4A, 5A, which means 10 minus 5, divided by 5, 1. So the acceleration is 1 meter per second squared. Yeah, and this is part B. Then when B has moved forward 20 centimeters, the string breaks. Find how much farther B travels before coming to rest. When they are asking in forces or pulley or connected particles something about distance or time or velocity, you have to remember that this is going to be a Suvat equation question, because it's going to be constant acceleration, and therefore we can apply Suvat. So this moves 20 centimeters, and then the string breaks, which means this tension disappears. And we need to see how much farther this box moves before stopping. Yeah. So if we apply Subat equation to that part of the motion, I'm going to write. Remember when we use Subat equations, it's good to write this way. They ask us the displacement. This initial velocity is when the string moves. So is the final velocity of, so this one is accelerating, the string breaks and then decelerates. Yeah. So this second part of the motion after the 20 centimeters is going to start with a velocity that is the final velocity of this first section. This has like two sections, one with acceleration and then one with deceleration. In the acceleration one, we know that it's 20, and we need to find the distance in the deceleration part, yeah, if that makes sense. So for this second part, the initial velocity is the final velocity of this one, so we need to find it. So we are going to apply this Subat is for the second part of the motion. So if we apply for the first part of the motion, and we apply Subat again, so let me write Subat again. The displacement is going to be the 20 centimeters. So like the first part of the motion and the second part of the motion. Displacement in meters is 0.2 meters. Initial velocity is 0 because it's released from rest. Final velocity is what we need because it's going to be our initial velocity here. Acceleration is the one that we found. So at the beginning, it's accelerating with 1 meters per second squared. So this is 1. And we don't need the time. Yeah. So we are going to look for a Subat equation without time, which is from the Subat. Remember, you have the Subat equations in your formula booklet. So you can pick one without time, which is this one. So V squared is what I need. U squared is 0. 2 times acceleration is 1, displacement is 0.2, so V squared is 0.4. We can find V, or just leave V squared, it doesn't matter. This is root of 0.4. Yeah. Final velocity in this second part of the motion is 0 because it's stopping. And the acceleration, we don't have it because it's decelerating. And the time, we don't have it, but we don't need it. If we want to find this displacement, we need the acceleration. Yeah, for every Subat equation, we can find something if we have at least 3 of the variables. So we need to find this acceleration. This acceleration, the only way of finding it is again with something similar to this. Yeah, so we are going to apply forces is mass acceleration. For this second part of the motion, I don't have tension anymore. Yeah, I don't have tension anymore. So if I apply my equation of motion for this one to find the new acceleration, I can say that this is new. I'm going to write that the resultant force, which is minus 5 newtons, is mass acceleration. Yeah, so that's the way of finding my new acceleration. So the resultant force is minus 5. Is going to be mass, which is 4, the new acceleration. And the new acceleration is going to be minus 5 over 4, or minus 1.25 meters per second squared. And it's minus because it's decelerating until it stops. So this is acceleration that I'm going to write here. Sorry. So minus 1.25. And again, I'm going to use the same Subat equation because I don't need the time and I don't have it. So V squared is 0, U squared is 0.4 minus 2 times acceleration S. Yeah, and from here I find S, and S is 4 over 25 or 0.16. This is meters. They don't ask us. Yeah, they gave us centimeters, so if you want, you can write this is 16 centimeters, but otherwise this is perfect. Yeah. So this is how much farther travels. Sometimes instead of how much farther, they ask you how much it travels in total. So you will have to add this to the 0 or the 20 centimeters that it moves at the beginning, but this is not the case. Yeah, they are asking just how much farther, so this is the answer. And what else? State one assumption you have made when finding your solutions in parts B or C. There is something that usually they tell us in these questions, which is that the string is inextensible, and they haven't said, they say slide the string, and they don't say anywhere that is inextensible. So we should say that we have assumed that, because if we don't assume that, we don't know how to answer these questions at this state. Yeah, so you can say that the string is inextensible, but I have here what the mark scheme says for you to see. So some of the things that you could say and they are accepted and they are going to give you the mark and are these ones. So no air resistance, for example, string remains parallel to the table, B doesn't reach the end of the table before stopping. Yeah, that's something that tells you in some of the questions. P does not hit the floor before a string breaks. Yeah, so this one doesn't hit the ground wherever the ground is. Yeah, and that's all with this exam question.